Now, as with functions, graphs are great. They help us understand things in a different way than formulas do, but we also need to have a way to manipulate vectors from a calculation perspective that without having to go to a graph or sketches of the arrows. The way we're going to look at vectors in most of our work is going to be a component perspective. The idea behind a component perspective is that we take a vector and we decompose it into components. That's the name. And those components that we pick are typically parallel to the x, y, and z axis. Certainly they will be in this course. For those taking algebra, you'll see fascinating other ways to talk about breaking down vectors. But for us, it's simply enough to take it in the x direction and the y direction and say, well, this vector can be composed of or has components of this x direction and this y direction, this amount in the y direction, this amount in the x direction. We're going to label some special vectors. We're going to call I with an arrow the vector along the x-axis, and it's going to be a vector of length 1. And I should put a little word in here. Definitely in the direction of the positive x-axis as opposed to going backwards, the negative x-axis. So everything's sort of a positive unit vector for these three quantities here, and we keep them in alphabetical order I, J, K. The idea behind that is if we think of our vector here, I can write it as some amount in the x direction and some amount in the y direction, which would be some multiple of, or some multiple of the I vector and some multiple of the j vector added together head to tail to generate the vector that we want. That's one typical way to write it. And another way, though, that's actually much more compact, once we do this 10 times with I, J, and K and I, J, and K every single time, we recognize that what really matters is how much of the I, how much of the J, how much of the K. That's what really defines the vector. If we know that it's always times I times J times K in that order. So we often will use component representation just by listing how much or how far in each of the component directions we have in our vector. We're going to see that play out. I think it's easier with examples. All right. Other textbooks may use different notation for this. We're going to try to stick with angle brackets to make it as clear as possible, or explicitly say I with a vector, J with a vector. All right. So let's take a look at some vectors and see how they might be represented. V1 is an easy one. Starts from here, goes to here. That would be two i's because it takes 2 steps to the right and has no j's. So that's V1. We could also write that as simply the 2, 0 vector. V2 would be the 1, 1 vector. Or we might just write it as I plus j. 1 step to the left, step to the right, that's I. 1 step to the up direction, that's j, or 1, 1. V3 would be down, x always comes first, so x is 1, and the downside, it's going downwards in the x direction, downwards in the y direction, -3. And last but not least, x first, -2, +2. That would be V4. And again, we could write it as -2 i's plus 2 j's if we wanted, and likewise, this could be an I minus 3j. Always with the hats on the i's and the j's, or the vector signs, to indicate that these are the unit vectors in the corresponding directions. Now what if we talked about V1, so V1, plus V3? Well, if we did a little head to tail setup here, like so, we could talk about V1 plus V3. Let's do it in color here. And you see what we did with that. Well, we took all of V1, which was 2 steps to the right, and then we took one more step to the right because V3 involved a step to the right. So the component side of this turns out to be really straightforward, which is why we like components when it comes to calculating values with vectors. The x component of the net vector comes from all the x components of the vectors I'm adding. I take the 2 and the 1, and I get a 3. I took 3 steps to the right. Now, what happened in the vertical direction? Well, there's no vertical change in the first vector. The second vector took us down 3. And so as a net result, we end up with the vector 3 in the x direction, negative 3 in the y direction, 3 in the x direction, negative 3 in the y direction. And that's exactly what we sketched out here. So the final vector we end up with is b. So that component notation, again, is there to reinforce the graphical side, or to be an alternative if it turns out we don't really want to go through sketching. We can still calculate the sum of vectors using components. As an extra practice here, what do you think v4 minus v3 would be when it's written in components? I'll give you a second to think about that, then we'll look at the solution. All right, v4 is negative 2, 2, left 2, up 2, and now we're subtracting v3, and v3 was the 1, negative 3 vector. So the naive, straightforward approach here would be say, well, I've got negative 2 minus 1, that'll be negative 3, 2 minus minus 3, that would be 5. Let's write that out actually in 2 steps. So take the negative 2 minus the 1, and 2 minus the negative 3, and that gives us negative 3, 5. Now that's on the list here, so I think that's right. Let's put the check mark there. But can we verify that graphically just to get some reassurance? Well, we had v4, and v3 would have been this vector here, but we're subtracting v3, so it's going to be that vector that works in the opposite direction. There we go. So we have v4 minus v3, and if we take the combination there, that didn't work at all. Let me try that again. Awesome. One more time. Fantastic. Close enough. All right. Oh God, it's awful. All right. Bear with me. There we go. That's v4 minus v3, and we see that it's negative 3 and up 5, negative 3 in the x direction, plus 5 in the y direction. And that matches exactly what we calculated using components. So we're reinforcing the duality between the graphical form and the notation that we're getting here. Okay. We've seen lengths of vectors on a page. We have components now in terms of their x and y directions. But what if we're talking about the magnitude or length of a vector, just the single length? What is the one length that describes a vector? Well, courtesy of Pythagoras, the length of a vector, and these double lines here means, or the definition of it means the length of the vector, or magnitude if we're talking about something where length doesn't make a lot of sense. It's like an absolute value. It's a size thing. Absolute value indicates how big is my number. The double bars here are typically used when you're talking about vectors. And notice it's just the two components squared, square rooted. So try this one out on your own. If I had a vector 2, negative 3, what would be the magnitude or the length of that vector? All right. This is a simple formula application. The length of the vector 2, negative 3 is going to be the square root of 2 squared and added to negative 3 squared, and that's the square root of 13. So always a nice positive quantity. Lengths are always positive here, so we get C as our answer.